right? So, very good morning to you all. I welcome you all for today's EMF class. Is my voice audible? You just text me. Yeah, thank you. In my last class, I have discussed reflection coefficient, how to calculate a reflection coefficient, and the derivation for the formula I have done in my last class. And before I start my class, one request from my side. I request everyone to join within time. So many of you are not joining in time. Almost I'm losing 15 minutes. So please keep this in mind. Even still, only 75 students were joined so far. So I request you all to join in time. Just a minute. Right. So you can go live in YouTube. You can watch it there. Right. So let me start today's session. Let me recollect what I have discussed in my last class. Reflection coefficient. So this is the derivation. So reflection coefficient is defined as the ratio between reflected voltage to the incident voltage, VR by VI, right? And from the transmission line equations, we have considered voltage equation, right? So from this, we have determined the reflection coefficient, right? So this is all the procedure which I have done in my last class. You can go through it, right? So this is the final expression. Capital gamma is equal to ZL minus Z naught by ZL plus Z naught is the expression for reflection coefficient, right? Where ZL is load impedance and Z naught is characteristic impedance, right? So that is what we have discussed in our last class, right? And today I'm going to discuss about um, I'm going to discuss one more new topic, continuation for this standing wave ratio, right? Standing wave ratio. So continuation for reflection coefficient is standing wave ratio, right? So when reflections occurs, whenever load impedance is not terminated by its characteristic impedance, right? When load impedance is not terminated by characteristic impedance of a transmission line, then we call the transmission line is a mismatched line, right? When load impedance is not terminated by characteristic impedance, we can say that the transmission line is a mismatched line, right? So mismatching in the sense load impedance not equal to source impedance. In other words, load impedance not equal to characteristic impedance. What happens when transmission line is mismatched? When transmission line is mismatched, only part of the power or voltage, right, whatever it may be, only part of it will be absorbed by the load, and rest of the part or maximum of the input will be reflected back, right? Maximum of the power or voltage will be reflected back. That is called as reflection, right? So when voltage reflected back, the reflected voltage will combine with the instant voltage, right? In other words, the reflected wave combines with the instant wave, right? The reflected wave combines with the instant wave, right? For example, if you consider a boundary like this, let us say this is the load, right? And let us say that load is mismatched, right? Load is mismatched when um, the input waveform meets the boundary, right? Like this, and let us say this is the incident wave, right? This is the instant wave. When load is mismatched, what happens? The wave will reflect back. The wave will reflect back. And so this is the reflected wave. This is the reflected wave, right? So the reflected wave, this is the reflected wave. Reflected wave. So reflected wave combines with the instant wave, right? Reflected wave combines with the instant wave and forms standing wave, right? And forms standing wave. Standing wave in the sense wave that does not move or wave that does not propagate is called as standing wave, right? So therefore, when the transmission line is not correctly terminated, when the transmission line is not correctly terminated, wave reflections take place, right? Wave reflection take place, right? The reflected wave combines with the incident wave and forms standing waves, right? Forms standing waves. If it is in terms of voltage, then we call it as voltage standing wave ratio, right? In terms of voltage, it is defined as voltage standing wave ratio, VSWR. If it is in terms of current, then it is called as current standing wave ratio, ISWR, right? Voltage standing wave ratio and current standing wave ratio, right? So therefore, voltage standing wave ratio, which is represented by small s, right? Which is represented with small s, and mathematically is defined as the ratio between maximum voltage to the minimum voltage, right? Maximum voltage to the minimum voltage, right? So whenever reflected wave combines with instant wave, there exists maximum points and minimum points, right? So this is the maximum voltage, and this is the minimum point, right? Minimum voltage point, maximum voltage point, and minimum voltage point. So therefore, the ratio between maximum voltage to the minimum voltage is defined as the voltage standing wave ratio, right? Now, let Vi is the incident voltage, and Vr is reflected voltage, right? Vi is instant voltage and Vr is reflected voltage. Then standing wave ratio S is equal to maximum voltage, right? Once again, let me write it. Maximum voltage to the minimum voltage, which is equal to maximum voltage in the sense Vi plus Vr, right? Instant voltage plus reflected voltage, right? Instant voltage plus reflected voltage, that is the maximum voltage, and the minimum voltage is Vi minus Vr. So we are taking the magnitude of the voltages, right? Mod Vi and Vr, right? So maximum voltage is sum of instant and reflected voltages. Minimum voltage is the difference between instant and reflected voltages, right? So that is voltage standing wave ratio, right? Now, for further simplification, let me write like this. S is equal to, let me take Vi common, right? So if I take Vi common, what we will get? Vr by Vi divided by 1 minus Vr by Vi, right? So taking Vi common from both the numerator and denominator, right? So taking Vi common, we will get this, and S is equal to 1 plus capital gamma divided by 1 minus capital gamma, right? Since capital gamma, what is meant by capital gamma? Is reflection coefficient, which is defined as reflected voltage to the instant voltage, right? In my previous class, I have discussed this. Reflection coefficient is equal to Vr by Vi, reflected voltage to the instant voltage, right? So therefore, this will give the relationship between, right? So this can be called as the relationship between, right? Relationship between standing wave ratio and deflection coefficient, right? So this is the relationship between VSWR and reflection coefficient capital gamma, right? So very important. Remember this formula. So small s, VSWR is equal to 1 plus capital gamma by 1 minus capital gamma, right? So here I have expressed voltage standing wave ratio as a function of reflection coefficient. In a similar way, I can express reflection coefficient, right? I can express reflection coefficient in terms of standing wave ratio, S minus 1 by S plus 1, right? So this is the reflection coefficient as a function of voltage standing wave ratio, right? So S is equal to 1 plus capital gamma by 1 minus capital gamma, and capital gamma is equal to S minus 1 by S plus 1, right? So this is about voltage standing wave ratio, right? I hope it is clear to you. Any doubts you have, you can ask me, right? So based on the so far discussion, let us consider a few so here I have taken two problems. First of all, let me do the second problem first, right? So what is the second problem here? Let me zoom in. Yes, right. So here, if reflection coefficient is 1 by 5, right? If reflection coefficient is given, which is equal to 1 by 5, right? And the corresponding VSWR small s is equal to how much, right? So what is the formula we have? S is equal to 1 plus capital gamma divided by 1 minus capital gamma, right? So this is the formula, and very simple. This is equal to 1 plus 1 by 5 divided by 1 minus 1 by 5, right? So if you calculate, you will get 3 by 2, right? So this is the answer, 1.5. The standing wave ratio is 1.5, right? So very simple, direct substitution, right? So similarly, coming to the first problem, a 30-meter long. First of all, note down the given data. Given data, 30-meter long. That means L is equal to 30-meter lossless transmission line, right? So lossless transmission line, right? And characteristic impedance Z0 is equal to 50 ohm at F is equal to 2 megahertz, is terminated with ZL is equal to 60 plus for J40, and V is equal to 0.6 V naught, right? So this is the given data, right? So find reflection coefficient, right? Find out reflection coefficient, voltage standing wave ratio, and input impedance, right? Reflection coefficient, voltage standing wave ratio, and input impedance, right? Reflection coefficient, capital gamma is equal to, what is the formula? ZL minus Z0 by ZL plus Z0, right? Very simple, right? So ZL is given, and Z0 is given, right? ZL is given, Z0 is given, and substitute, simplify, we'll get the answer directly, right? So very simple, right? And the answer will be, I will give you the value 0.3523, and 56 degrees. You can also determine the angle of reflection, right? At what angle is reflected. And similarly, standing wave ratio, voltage standing wave ratio. If we know reflection coefficient, we can determine standing wave ratio, right? So because we know the relationship between, right, 1 plus capital gamma divided by 1 minus capital gamma, right? So we know reflection coefficient and substitute reflection coefficient in this formula and simplify, you'll get voltage standing wave ratio, right? So similarly, input impedance, right? So input impedance, which formula you will take? Input impedance of a lossless transmission line, right? So for a lossless transmission line, input impedance, what is the formula? Z0 ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L, right? So this is the formula, right? Input impedance of a lossless transmission line, right? So here I think everything is clear here, right? So ZL is known, ZL we know, Z0 is known, and whereas beta L, right? Beta L. So what is beta L? Beta 2 pi by lambda into L, right? Beta is 2 pi by lambda, right? So is equal to 2 pi by lambda into L. L is given. What is L? 30, right? 30 meters long transmission line, and 2 pi by lambda. How do you determine lambda? So wavelength lambda is equal to C by F, right? So C means what? Velocity, right? So C or B, sometimes it is represented with C and sometimes it is represented with V, both are same. So this is equal to 0.6 V naught divided by F, right? And where V naught? V naught is velocity in free space, 3 into 10 power 8 meters per second, right? V naught is 3 into V naught is equal to 3 into 10 power 8, right? So substituting that, and frequency is given 2 megahertz, and simplify, you'll get lambda, right? So substitute lambda here in this expression and simplify, you will get beta, right? And substitute beta here, right? Substitute beta here, beta L here, and substitute ZL, Z0 and simplify, right? And simplify, you will get the answer, right? So the answer will be 23.97 plus J 1.35 ohm. So this is the answer, right? So if you do so, you will get this answer. I request everyone to do it, right? So do it later, right? So these are some of the example problems, right? So let me switch on to another topic: open circuit and short circuit transmission lines, right? Open circuit and short circuited transmission lines, right? So this is one more interesting topic: open circuited and short circuited transmission lines, right? So far we know input impedance, which is equal to Z0 ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L, right? I'm considering lossless transmission line, right? So I'm considering a lossless transmission line. And similarly, reflection coefficient is equal to ZL minus Z0 divided by ZL plus Z naught, and voltage standing wave ratio 1 plus capital gamma divided by 1 minus capital gamma. So these are the three important parameters we know regarding transmission lines, right? So now let us consider a um, let us consider case one. Case one: short circuited transmission line, right? Short circuited transmission line. What is meant by short circuited transmission line? We know that. So this is the transmission line, right? So input voltage, and this is ZL, right? Load. So what is meant by short circuited transmission line? Short circuited transmission line in the sense load is shorted, right? Load is shorted like this. Load is shorted. So load is shorted in the sense what? ZL is equal to 0, right? Load impedance is 0. So when load impedance is equal to 0, we can say that the transmission line is short circuited, right? So therefore, the transmission line is short circuited when ZL is equal to 0, right? When ZL is equal to 0, right? So when ZL is equal to 0, input impedance, right? Input impedance of a short circuited transmission line. So what will get? When ZL is equal to 0, right? So we have the formula, right? So you can see here the formula. So in this formula, substitute ZL is equal to 0, right? Let me, for convenience, let me write once again. Z naught ZL plus J Z naught tan beta L divided by Z naught plus J ZL tan beta L, right? So this is the input impedance. So now ZL is equal to 0, right? ZL is equal to so this is 0, and this term is 0, right? So what will get? What will get here? If this term is 0, Z naught and Z naught will get cancelled, and we will have J Z naught tan beta, right? Input impedance is equal to J Z naught tan beta. So therefore, for a short circuited transmission line, the input impedance is Zn is equal to J Z naught tan beta L, right? So similarly, reflection coefficient, right? So what is reflection coefficient? If you substitute ZL is equal to 0, right? So reflection coefficient capital gamma is equal to -1, right? We get -1. And similarly, here standing wave ratio. So standing wave ratio, what will get? Standing wave ratio 1 plus 1 divided by 1 minus 1, right? So something by 0, right, is infinite, right? Is infinite. So therefore, standing wave ratio is infinite. right? Standing wave ratio is infinite, right? So reflection coefficient is 1, right? Reflection coefficient is 1 in the sense what? Reflection coefficient is 1 in the sense the entire wave reflected back, right? Because the transmission line is short circuited, the entire wave reflects back, right? So reflection coefficient is equal to 1 means the entire wave, I'm using the word wave here, right? It may be voltage or it may be current, right? Whatever it may be. So when reflection coefficient is 1 means the entire wave reflects back. The entire wave reflects back, right? Minus 1 in the sense, here you can see minus 1. Minus 1 in the sense with phase shift, right? Minus 1. Capital gamma is equal to minus 1. Minus in the sense phase shift, right? Phase shift. The wave reflects with phase shift, right? The wave reflects with phase shift, right? So capital gamma is equal to 1 in the sense without phase shift. Capital gamma is equal to minus 1 in the sense with phase shift, right? So this is about short circuited transmission line, right? And one more thing, you can draw the variation of input impedance, right? The variation of input impedance with respect to here, this is 0, right? And let us say on y-axis impedance. So this is the input impedance of short circuited line. So therefore, this can be written as Z suffix SC, right? Short circuited Z suffix SC. Therefore, on y-axis, variation of input impedance of short circuited transmission line, and on x-axis beta L, right? Beta L, right? So with respect to beta L, how input impedance varies, right? How input impedance varies, that we will see. And let us say here beta L is equal to 0, and this is beta L is equal to pi by 2, and this one is beta L is equal to pi, and this one beta L is equal to 3 pi by 2, and beta L is equal to 2 pi, right? So at different values of beta L, how input impedance varies, right? How input impedance varies, that we will see, right? So here when beta L is equal to 0, right? When beta L is equal to 0, when beta L is equal to 0, that means what? Tan beta L, which is equal to tan 0, which is equal to 0, right? Beta L is 0, therefore tan 0 is 0, therefore input impedance of short circuited transmission line is 0, right? So when beta L is equal to 90 degrees, when beta L is equal to 90 degrees, tan 90 is infinite, right? Tan 90 is infinite. So therefore, input impedance of short circuited transmission line is infinite. So therefore, the input impedance varies like this. At beta L is equal to 0, and at beta L is equal to pi by 2, the input impedance varies like this. So this is infinite, right? Plus infinite, right? So therefore, this one positive, right? Positive section is called uh, inductive, right? Positive section is called inductive. So this one, this is inductive, and below is capacitive, right? So between 0 and pi by 2, right? Between 0 and pi by 2, the impedance is inductive, right? Between 0 and pi by 2, the impedance is inductive, right? And um, and now here, so immediately after 90 degrees, right? Immediately after 90 degrees, so for example, 90.1, right? So at 90.1, tan 90.1, right? Immediately after, whatever the value, you can take it, even it is 90.01, 90.02, right? Immediately after 90 degrees, right? Tan 90 is minus infinite, right? Tan 90 is minus infinite, right? And similarly, when beta L, right? When beta L is equal to 90.5, tan 90.1 is equal to minus infinity. And similarly, when beta L is equal to pi, tan pi is equal to 0, right? Tan pi is equal to 0. So therefore, the variation, right? So here, the variation will be like this. So here, immediately after 90 degrees, it is minus infinite, and when beta L is equal to pi, it is 0, right? So therefore, this is the input variation, right? So between 0 to pi by 2, it is inductive, and between 90 degrees to 180 degrees, the input impedance of a short circuited transmission line is capacitive. And similarly, so on and so forth, if you do it, and again, you will get, the wave will be repeated like this. And similarly, in between this, you get this one, right? So this is how the input impedance, right? Input impedance of a transmission line varies, right, with respect to beta L, right? So this is how we can draw the graph, right? So similarly, let me discuss the remaining also, right? Case 2, let us consider case 2 here. Case 2, open circuited transmission line, right? Open circuited transmission line. The transmission line is open. This is the transmission line. Let me draw once again. So this is the load, right? And this is the input voltage. The transmission line is open circuited. That means what? Load is open. All right. That is, load is open, right? Load is open in the sense what? When load will be open? When ZL is very high. That means infinite, right? So therefore, the transmission line is open circuited when ZL is equal to infinite, right? When ZL is equal to infinite, right? So for this case also, let us try to determine input impedance. So input impedance is equal to Z0 ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L, right? So this is the formula for input impedance, as we know, right? And now ZL is infinite, right? So therefore, what I will do is, let me take ZL common, right? Let me take ZL common from both numerator and denominator. I will get 1 plus J Z0 by ZL tan beta L divided by Z0 by ZL plus J tan beta L, right? So this you'll get by taking ZL common from both numerator and denominator, right? Now, when ZL tends to infinite, right? When ZL tends to infinite, what happens? When ZL tends to infinite, then we can say that this term, right? So this term will be 0 and this term will be 0, right? When ZL tends to infinite, those two terms will become 0. So therefore, we have, right? We have Z0 by J tan beta L, right? So this can be written as Zn, which is equal to ZOC, right? Is equal to minus J Z0 cot beta L, right? So this is the input impedance of a open circuited transmission line, right? Minus J Z0 tan beta cot beta L, right? Is the input impedance of open circuited transmission line, and Zin is equal to J Z0 tan beta L, right? Is the input impedance of short circuited transmission line, right? And this is the expression for input impedance of open circuited transmission line, right? Similarly, reflection coefficient. So what is reflection coefficient? Is equal to ZL minus Z0 plus ZL plus Z0, right? So this we know. So this is the formula which we know. Here I have taken ZL minus Z0 by ZL plus Z0, right? So let me take ZL common here also. What I will get 1 minus Z0 by ZL divided by 1 plus Z0 by ZL. So ZL is infinite. So therefore is equal to 1. So therefore reflection coefficient is equal to 1 plus 1 here, right? So whereas for short circuited transmission line, it is minus 1, right? For short circuited transmission line, it is minus 1, whereas for open circuited transmission line, it is 1. That means here also the entire wave reflects back, right? Here also the entire wave reflects back, but without phase shift, right? Without any phase shift, right? And similarly, voltage standing wave ratio S is equal to what we will get. S is equal to um, here infinite, right? Same you'll get, right? So because 1 plus S is equal to 1 plus capital gamma divided by 1 minus capital gamma. So therefore denominator is 0. So therefore voltage standing wave ratio is infinite, right? Therefore input impedance of an open circuited transmission line is this, that is minus J Z0 cot beta L, and this is the reflection coefficient, standing wave ratio, right? Now let us see how input impedance varies, right? How input impedance varies with respect to beta L, that we will see, right? So um, I will close within 10 minutes, right? So on x-axis beta L and on y-axis ZOC. This is 0. Beta L is pi by 2. Beta L is pi. Beta L is 3 pi by 2. And beta L is 2 pi, and so on, right? So let us verify how the input impedance of open circuited transmission line varies with respect to beta L, that we will see. Right? So now when beta L is equal to 0, what happens? When beta L is equal to 0, right? So cot beta L is infinite. right? So we know it is exactly opposite to tan, right? Cot is opposite to tan, right? So therefore, here we'll get infinite. When beta L is equal to 0, we'll get infinite. Therefore, ZOC is equal to minus J Z naught cot beta L. So therefore, minus infinite, right? When beta L is equal to 0, ZOC is minus infinite, and when beta L is equal to 90 degrees, ZOC is equal to 0. So therefore, the variation, the input impedance varies like this with respect to beta L, right? So similarly, immediately after, in between 90 degrees and 180 degrees, it varies like this, right? So in between pi and 3 pi in like this, and in between 3 pi by 2 and 2 pi is like. So this is how the input impedance varies, right, with respect to beta, right? So exactly opposite. So 0 to 90 degrees, it is inductive, and 0 to, sorry, it is capacitive, right? So in between 0 to pi by 2, it is capacitive, and in between 90 degrees and pi, it is inductive, right? So opposite here, whatever the waveform here we have seen, and this waveform is exactly opposite, right? So this is about open circuited and short circuited transmission line, right? And now let me also consider one more case. With that, I will close the session, right? So let me consider one more case, that is case 3, right? Case 3, uh, matched transmission line, right? Matched time. We have seen open circuited transmission line, that is ZL is equal to infinity. We have seen short circuited transmission line, that is ZL is equal to 0. And now we are looking at matched transmission line. Matched transmission line in the sense, when the load impedance is terminated by its characteristic impedance, it is called as matched line, right? So that means here, this is the load ZL, right? And this is the input of the transmission line. So the transmission line is said to be matched line when ZL is equal to Z0, right? The transmission line is said to be matched line when ZL is equal to Z0. So when ZL is equal to Z0, what is input impedance? So input impedance is equal to Z0, ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L, right? So when ZL is equal to Z0, what happens? When ZL is equal to Z0, we can say that numerator and denominator will get cancelled, right? Numerator and denominator will get cancelled, and we have Zin is equal to Z0, right? So if we combine these two, Zn is equal to Z0 and ZL is equal to Z0, therefore ZL is equal to Z0, which is equal to Zn, right? That means what? ZL is equal to Zn, right? So that means when load impedance is equal to input impedance or source impedance, right? Or ZL is equal to ZS, source impedance. When load impedance is equal to source impedance, then we can say that the transmission line is matched. When transmission line is matched, we can say that maximum power will be transferred, right? So in this case, what is reflection coefficient? Capital gamma is equal to ZL minus Z naught by ZL plus Z naught. What will get? ZL is equal to Z naught, therefore 0, right? So reflection coefficient is 0, right? So far for open circuited transmission line and short circuited transmission line, reflection coefficient is 1, right? 1 and minus 1. But whereas here reflection coefficient is 0. Reflection coefficient is 0 in the sense what? No reflections, right? No reflections takes place, right? When there are no reflections, right? When there are no reflections, what is standing wave ratio? So standing wave ratio is 1 plus capital gamma divided by 1 minus capital gamma, which is equal to 1, right? So therefore, very important, capital gamma reflection coefficient is 0, right? And standing wave ratio is 1, right? ZL is equal to ZS. ZL is equal to ZS. Reflection coefficient is 0, and standing wave ratio is 1, right? So perfect transmission line, right? No losses and perfect transmission line, right? So therefore, whenever the transmission line is matched, then reflection coefficient should be 0 and voltage standing wave ratio is 1, right? So voltage standing wave ratio is the direct measure of loss, right? Voltage standing wave ratio, right? So VSWR is the direct measure of loss in a transmission line, right? So S is equal to 1 means no losses, right? S equal to 1 means no losses, right? So this is about transmission, open circuited, short circuited, and matched lines, right? So this let us close the session.